Let me briefly explain about our report of the I-35W Bridge collapse in 2007. The main causes were weak disease plate, lack of backup support, and too much weight for repairs. Poor maintenance also play a role. To prevent similar failure, we recommend a few key solutions. First, use stronger and safer structural design. Second, perform regular inspection to catch early sign of damage. Third, protect bridge foundations from erosion and install sensors to monitor bridge health in real time. Lastly, improve teamwork between agencies for better decision making. Highway bridges are essential to modern transportation system. They must remain in steady equilibrium under different types of load, such as dead load, life loads, environmental loads like wind or temperature change, and sometimes even construction load. If these forces are miscalculated or misplaced, the bridge structure can become unbalanced and fail. A tragic example is the Interstate 35W Bridge collapse in Minneapolis on August 1, 2007. This steel deck truss bridge was 1,907 feet long and carried 8 lanes of traffic. It served over 140,000 vehicles per day, making it Minnesota's third most used bridge. On the day of the collapse, a construction crew have closed 2 lanes and placed heavy materials like sand and concrete on the deck for repairs. This added weight combined with live traffic and the bridge on dead load caused excessive force at critical joint known as U10. This joint had undersized gusset plates, only 0.5 inches thick. Due to a design error, when overloaded, this point failed. At 6:05 p.m., during evening traffic, 456 feet of the main span collapsed from a height of 108 feet, sending 111 vehicles into 15-foot deep Mississippi River. The disaster caused 13 deaths and 145 injuries. According to National Transportation Safety Board, the main cause was the insufficient gusset plate capacity, made worse by the added construction load. It violated basic static principle. The force and moment were no longer balanced. The collapse showed how a small design mistake in one joint can trigger the failure of the entire structure. It taught engineers the importance of correct free body diagrams, accurate force calculation, and maintaining safety margin in all structural design. Most importantly, it highlighted how theory and static calculation must be applied carefully in real-world engineering to avoid future tragedies. Based on this case, our report focused on 3 main engineering scopes. First, to review the original load case, including the dead load, live traffic, and construction materials. Second, to analyze the critical joint U10 using statics principles like free body diagrams and equilibrium equation. And finally, to propose improvement using stronger gusset plan, better load distribution, and regular inspection protocol to ensure every joint is stratified, total force equal to 0 and total moment equals to 0. By achieving this goal, we can help prevent similar failure and improve the safety and lifespan of future bridge design.
The bridge collapse was triggered by long-standing design issues combined with increasing load over time, and the most critical flaw is actually the undersized gusset plates at node U10, which were only half the required thickness. These gusset plates play a key role in holding the truss together by transferring forces between members. Under normal conditions, they were already overburdened with axial and bending forces. Over the years, the bridge dead load increased substantially due to renovations such as thick concrete overlay in 1977 and a heavy medium barrier in 1998. These modifications were added without re-evaluating the structural capacity, which then, on the day of the collapse, temporary construction equipment and materials added over £500,000 of concentrated weight directly over the already compromised U-turn gussets, which acted as the final overload condition. The final failure involved more than just load. It was a breakdown in structural equilibrium. One overload factor was frozen bridge bearings, which blocked the bridge's natural expansion in hot weather. This added extra axial force into the truss system, which particularly affects already stressed gussets connections. When the U-turn gussets fractured, the bridge lost its internal balance. Load that was already evenly distributed rapidly got shifted to adjacent members, including the L9 and U10W, which then buckled laterally due to increased compression. From here, the bridge entered a state of dynamic instability, collapsing under 4 seconds. The failure shows how the combination of design oversight, cumulative loading, and impaired equilibrium can have catastrophic consequences when not addressed in time.
This slide highlights the key external factors that contributed to the bridge collapse. First, we have overloading. During maintenance, around £580,000 of construction materials were placed directly over the bridge weakest point, the U10 gusset plates. This means the bridge couldn't handle the localized stress. Next, thermal restraint played a role. Corroded bridge bearing froze in place, preventing the steel structure from expanding under the summer heat. This caused additional compressive stress on already vulnerable joints. Lastly, environmental neglect. The bridge has visible corrosion and aging components, but maintenance and upgrades were not prioritized, further weakening structural integrity over time. Now let's look at the internal systematic oversights. The core issue was a design flaw. The gusset plates at key joint like U10 were too thin from the beginning, just half the thickness they should have been. With no redundancy in the designs, one failure cascaded into a full span collapse in under 4 seconds. Secondly, inspections and regulation gaps allowed problems to go undetected. Over the years, the bridge load increased by 20%, but no revaluation of the gusset plates was ever conducted. Standards at the time didn't require it. Lastly, there was a lack of structural monitoring. No real-time sensors or warning systems that could alert engineers about rising stress or fatigue in critical parts of the bridge.
Now I'm going to talk about some recommend for the trust bridge disaster. First of all, we need to detect and correct before the design had made final. And secondly, we should verify and calculate the appropriate design before we perform on this project. Thirdly, based on this, the U10 gusset is based on corrosion. Maybe we need to detect the plant corrosion in the future. And the second part, I'm going to talk about how to connect with the administration and institute training courses for engineers. First of all, we need to update National Highway Institute training courses. Secondly, we need to do some revision to the referenced materials. After that, we also need to work with the administration of highway to develop and implement the pre-design quality. After that, also the manual for the bridge evaluation, including the capacity of gas plates as part of the loading rating for non-load path reductant truss bridge. Not only this, and also need to update the manual for the bridge evaluation, is also a very important chain in the manufacturing. Finally, for the construction part, we need to ensure the raw materials placed on the construction or maintenance project do not overload the structure members or their connections, because of the construction members need the time to figure everything out. We need to give the enough time to finish the project. Finally, do some recap is you need to recognize and responding to the potential damage and reverse the actual guide to incorporate new information. I hope in the future this kind of disaster will not happen, and people work together to get more valuable and implement the design more quality and safety. That's all. Thank you.
Summing up, the Interstate 35W Bridge accident wasn't just an accident. It was a tragic engineering failure caused due to inadequate inspection and maintenance. And also, applying theoretical calculations in real life without considering real-life factors like temperature change and fluctuating loads eventually caused this bridge to collapse, as the force and momentum weren't in equilibrium anymore. So, this tragic accident was actually in fact an engineering failure, which is why the future engineers need to be careful to avoid this kind of failures for public safety. In future, to avoid this kind of failures, we must keep our designs simple, which is easier to calculate and easier to maintain, and also we must be careful to use the best materials for our design, as materials have a very good impact on our designs. Thank you so much.